Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, let's continue our computational fluid dynamics CFD tutorials. In this video, we're gonna talk about a very important application. We're gonna talk about the lithium ion battery and the ways or the techniques that are used to cool the pack of this kind of battery. It's very critical application, and it's used nowadays for the electric vehicle or electric car. So let's get started. Battery, yes, you find here this kind of battery, many designs, or find actually many designs, many packs, and cylindrical and also rectangular. Here ion battery, electric car, electric vehicle. Okay, you will find many topics about it, and also you can find many videos on YouTube. You'll find here on battery car. Find here many videos about it. Okay, so please, you have to watch these things and check out many things. Also, we're gonna talk about the heat transfer and the cooling techniques. So of course you should know the fundamentals of the heat transfer, and this is one of the simplest references that you can get. And we have find here steady heat conduction, also for the walls, for the resistances, and also transient heat conduction. Here it's very simple, by the way, and the numerical methods in heat conduction. Why numerical methods? Numerical methods means CFD, and here the computational fluid dynamics. Here is very important to know these kind of things. And the numerical grid, and these kind of things. Here are the boundary conditions. Of course, the finite difference formulations of differential equations, one-dimensional steady-state conduction, two-dimensional steady-state conduction, okay, and here transient conduction, and so on. And here are the fundamentals of convection, and you must get a moving fluid, of course, very interesting, and the boundary layer, the thermal boundary layer, and how it affects the convection or the heat transfer by convection, and here external forced convection, imperial flow over flat plates, and so on. So please, gentlemen, you must read these kind of things. The main topic now is we're gonna use Ansys Fluent Advanced add-on modules to simulate the battery, lithium ion battery. So you'll find here Ansys Fluent add joint solver for the optimization of the airfoils. I think we'll find many things about it, and also Fluent battery module, and this is our main topic, and Ansys Fluent continuous fiber module, and Ansys Fluent fuel cell modules, Ansys Fluent and the magnet or hydrodynamics, magnetohydrodynamics MHD module, and Ansys Fluent population balance module. You can check out all these kind of things by yourself later. And here is for the battery. Okay, let's get some theoretical knowledge. The application of lithium-ion batteries has been rapidly expanding from electric appliances and electronic devices to hybrid electric vehicles and electric vehicles due to their high energy density. The main concerns when designing a lithium-ion battery are its performance, life, and safety. So the Ansys Fluent battery models allow simulating a single battery cell or a battery pack using CFD technology to study their thermal and electrochemical behavior. So in this video, we're going to talk about how to simulate a single battery and a battery pack using two different designs. The Ansys Fluent battery models are provided as add-on modules with the standard Ansys Fluent licensed software, so you must write a line to define or to add on this feature. So we have here single potential empirical battery model and dual potential MSMD battery model. We're gonna simulate the battery using the dual potential MSMD. Also, you can find here a very interesting video uploaded by Ansys. Okay, ECM battery Fluent. You'll find here this is very interesting and very good video, but it's only used for showing the setup in Fluent, but I'm gonna show you the procedure from scratch from the geometry and meshing. Okay, so here, so single potential empirical battery model is useful if the geometries of the current collector, electrodes, and separator can be fully resolved. One potential equation is solved in the computational domain. This model is best suited for electrode scale predictions in a single battery cell. The model, however, has a limited ability to study the full range of electrochemical phenomena in battery systems, especially systems having complex geometry. When constructing a battery cell, the anode, separator, cathode sandwich layer is usually wound or stacked up into a jelly roll or a prismatic shape. It would be very expensive to resolve all the layers explicitly, even for a single battery cell. Furthermore, many industrial applications use a battery pack consisting of a large number of cells that are connected in series or in parallel. So the Ansys Fluent dual potential multi-scale, multi-dimensional battery model overcomes these limitations. That's why we're gonna use it right now by using a homogeneous model based on a multi-scale, multi-dimensional approach. In this approach, the whole battery is treated as an orthotropic continuum. Thus, the mesh is no longer constrained by the microstructure of the battery. Two potential equations are solved in the battery domain. To fit various analysis needs, the model includes three electrochemical submodels, namely the Neumann, Tiedemann, GU, and Kim. NTGK empirical model, the equivalent circuit model ECM, and the Neumann's pseudo 2D P2D model having different level of complexity. The model offers you the flexibility to study the physical and electrochemical phenomena that extend over many length scales in battery systems of various arrangements. And here in the general procedure, start Ansys Fluent, read the mesh file, and we're going to talk about these kind of things in details and then the next couple minutes. And here installing battery, okay. And here the anode cathode separator, negative, positive. And here are the equations. Please, you must read these lines to know what's going on and what are behind the scenes. And the thermal and electrical coupling, and the temperature, dependent electric conductivity, and these things. And here using the single potential empirical battery model, we have to learn these kind of things. Okay, I'm gonna cover this right now, and here is the theoretical. Also here the dual potential MSMD battery model theory and the equations that are used. Okay, and DOD is right here the depth of this charge also, and Y and U, and electrochemical reaction Q. That's why we need to cool the battery due to the heat generated. And we find here is alpha is a specific area of the electrode. So I'm gonna let you study these kind of things by yourself. And here is the circuit of the battery, electric circuit used in the ECM model. And here are the Newman's P2D model. Okay, and how it works, and coupling between CFD and submodels, and battery pack simulation. We have here packs. Okay, we're gonna use the bus bar to connect 1 2, and then here the positive and the negative, so you can make a pack. I have real connections and virtual connections. Okay, external short circuit, internal short circuit, using the dual potential MSMD battery model. Okay, here are the settings. Okay, for the cooling, we're gonna have here a paper that shows the cooling. Here is a single battery, positive and negative tab. Here is the voltage experimental, and here is the simulation with the experimental. Gentleman here is choosing a proper cooling method for a lithium-ion battery pack for electric drive vehicles, and making an optimal cooling control strategy to keep the temperature at optimal range 15 Celsius to 35 Celsius, essential to increase safety, extending the pack surface life, and reducing costs. So that's why you must know the boundary conditions and measure them, and know what is the optimum range of the temperature. Okay, so we have here the cooling techniques, conversion of air cooling like this, and here conversion of fin cooling, conversion of indirect and direct liquid cooling, and conversion of direct liquid cooling, and many things. We're gonna cover one of them. Okay, and also we have here some PDF, some documents that you can get from Google easily, and you have to check them out. Okay, so now let's get started. We have here the geometry. So we have here the geometry. Just I created this geometry in Autodesk Inventor, and I imported them as XT file. So we have here just a simple rectangle, and I extruded it. Okay, we have here the thickness just 2 millimeters. Have used by the way a very thin battery, and the dimensions here are random, so please you must be sure about your design. XT for the active zone, and it is add material, be careful. And here is the tab, the negative tab, it's add frozen. Okay, and the positive tab, it is also add frozen. If you imported all the XT files as add frozen, it will not work because you will not be able to define the zones later in Fluent. So please, here is add material, add frozen, add frozen. Okay, now we have three parts. Okay, in Autodesk Inventor. So we have here just a rectangle with extrude command, and here the positive tab and the negative tab, and you also can export each one of them as CAD format and XT file. Okay, and here is XT, and that's it. So after this, you close the geometry. Please be careful. The Okay, I'm gonna reset this. I've just duplicated it, so to start from scratch, to show you the steps, I have to reset them. Be careful, the negative tab and positive tab must be in contact with the active material to be sure of the connectivity. Okay, we are ready. Notice that when I designed the active material, we have here the geometry, solid one. Okay, notice that here the contact, you have to be careful, please. You must make it like this. Exactly, it touches. We have here the inner face, so this is the inner face. Okay, if this tab is far away from this, it will not work. Exactly like the realistic situation. So now the second important thing is to make this solid. Okay, solid, solid. Do not set it as default. No, solid, solid, solid. To tell Fluent that we're gonna deal with solids and to be able to define the zones. Here the sizing, I'm gonna make it fine and make it 1 millimeter as an initial guess. Do not use this setting. You must carry out a mesh dependency study, of course, according to the suitable size for your study. You have to get some knowledge about meshing. You can check out meshing here, thermal analysis and mesh size. Okay, in Fluent and something like this. You must know how to get the suitable meshing mesh size. I'm just showing you the method, and you must carry out mesh dependence study by changing the mesh size and compare between the results. Okay, so the most important thing now is the quality. The skewness in Fluent must not exceed 0.98. So the maximum skewness is very small. Okay, and here the statistics 31,635. Okay, so now this is maybe the negative tab. in or tab in, tab negative, tab positive. Okay, and here is the cell or the active zone, just a cell. So this is the cell, and we need the positive, or the negative. So all. Okay, here is, or general, it's better to make this in zone, and here is tab positive zone, and here is the cell. Okay, and then here is the negative, so here is tab in, and here is tab P for the positive and negative connectivity. Okay, so we have here tab, here is the positive zone, the negative zone, and the cell, and the face, the negative, and face of the positive. Okay, so now close. We are here. Okay, we're gonna update this. Okay, after updating, open setup. Of course, it is recommended to use double precision to increase the accuracy of the model. According to your CPU, you may use it serial, or if you have many count of the mesh size, you can use the Pearl. Here I have 4 processors. I'm sorry, I have 4 cores as maximum, so I can use 3, or I can use all the maximum, but I'm gonna use the serial right now. It's no need. So opening Fluent here. Okay, after done, define models add on module. Click enter, and we have here all the models add-on: MHD, fiber, fuel cell, SOFC, model with the unresolved electrolyte, population balance, adjoint, single potential barrier model, dual potential MSMD barrier model, PEM fuel cell model, and so on. Okay, a macroscopic particle model. We're gonna use 8. So now it's being loaded. Okay, loaded. We have here the models. We'll find this. Before defining it, you will not be able to use it. You will not find it. Okay, but now it's available. So open and enable. And we have here the models that we have just talked about. E-chemistry models, NTG, K, and so on, and user defined. And we have, you must please check out all these kind of things before using it to know how to simulate your battery. Okay, now we're gonna use this 0.3. It's like the tutorial that we have seen in the video, and here the initial depth of discharge, I think it was 0.5, and here is 1051, and for the U coefficients and Y coefficients, you can get it from the experiment that you must carry out, or by any other method, but it must be suitable for this battery. Okay, these coefficients are very critical. We have here the conductive zones. If you do not do what I have just said, add frozen and add material, and making them all of them are solid, you will not be able to see this view. You will find them here without any words. Okay, so the active components, tab components, and the bus bar components. First of all, bus bar components are only used, I think, for the pack simulations, so we're not gonna use them right now. Here, the active zone is just the cell, and the tab is tab zone, positive and negative. Now, the electric contacts. If you wanna make the resistance, you can make it here, but if you do not know it, just leave it as it is. And also you can check out use virtual battery connection for the user guide. I'm not gonna use it right now. Here the negative tab and here the positive tab. Now we can say that we are ready. So print battery system connection information. This is very important because if you have a mistake, you will know. Just click on it. Okay. Notice that active zone. Find here that no problem. Initializing battery model, number of required UDM is 32, and total collector tab area, and so on. We have N tab active and P tab. Okay, so number of battery series stages 1, number of batteries per just 1. Okay, if you have a problem, you will know. Just click OK. Now I'm sure that the battery is okay. Now go to the materials, and for the solid we're gonna define a material for the cell and for each tab or for the tab. Okay, the active material, the information that I'm gonna use right now is from the video by Ansys 20. Okay, here the UDS diffusivity, we're gonna use the defined per UDS for the positive and negative electrode, and you can check out the video. So here for the positive electrode, okay, and this, okay, and click OK. No, I'm not gonna overwrite aluminum. So we have here E material, okay, and we're gonna use another material for the tab zone. We're gonna copy the copper and modify it. Here is the copper T material. Okay, UDS, we're not gonna use the defined per UDS. We're gonna use defined for the battery E cond. Okay, this is the user defined by Fluent itself. Yes. So now we have here the T material, and it has one for the electrical conductivity. Just to close, now the zones, we have the cell. The cell is active material. The tab zone, the T material. E zone, the T material. Okay, now for the boundary conditions, we now here where is the wall cell where tab those are the three walls that we have here. Wall cell, sorry, we have to, before this, make it transient, and the equations, sorry, the models must check on the energy equation. And now we have the wall of the cell. Yes, this is what I'm gonna do. We have here the convection watt per square meter Kelvin. Heat transfer coefficient, we're gonna be 5. You have to know exactly the amount of heat transfer from the battery. That's why we need to cool it. Okay, and we have here 300 Kelvin. This is exactly like the tutorial. You must know this kind of inputs from the experiment. I'm gonna copy these boundary conditions for the other tabs. Okay, yes, gentlemen, I repeat, this is just for this tutorial. You have to know exactly what's going on with your battery. Okay, now we have finished these kind of things. Now we're gonna initialize the simulation, but before this we do not have here, we only have the energy and potential phi positive and potential phi negative. No need for the flow equation, and no need for the residuals for this battery. But we're gonna talk about cooling. We will need to define or use the flow equation from of Stokes equations to simulate the air or the water or the coolant for the simulations. But now we do not need it, so just initialize. Okay, Harsh is done. Okay, no problem. Exactly like the tutorial, the time step here is gonna be 30 seconds. The steps is 50, and maximum iterations, the more you have, the more accurate you get on the results. But we're gonna make it just calculate. And we have here the energy and UDS and the other equation. Okay, gentlemen, I have just finished this tutorial, this simulation. Okay, so let's go and see the contours. Go to the scalars, potential, positive, tab positive, hold tab positive, and the cell zone, and then display. So we have here, okay, find here is 3.8, okay, and here from the tutorial found 2.99, and here is 2.997 multiplied by E. Okay, so 2.998, and here is 2.997. The variation is not high. Here it's for the positive. Can make it like this. .8. Of course, this slightly different from this value. Why? Because the geometry is not the same. So let's get the negative. and here the negative, we find it's 0. Okay, look. So okay, so also you can check out the vectors of the current density, memory, magnitude, exactly like this for the tab and the wall active. So here is wall, just display it. Okay, we'll find here the current density. Look, and here the flow of the current. Okay, so gentlemen, you can see here is 4.375 for the current density. Also can see here 2.47 to multiply by e to the power 4 here to the power 5. Okay, this is due to, like I said, the difference between the two models, and we have here negative electrode. So this is the negative and the other is the positive. Okay, and then the current moves and then it enters the circuit. Okay, so we have just finished this simulation. Now we're going to talk about the cooling, and we're going to talk about another many things. So just close Fluent. Just duplicate this project. So now we have here cooling. Okay, open the geometry. Now here the same, so just we need to make a channel. Just select this face and make extrude direction vector. It's like no direction vector. It's like this. Okay, apply. It's gonna be 5 millimeters, and it's gonna be at frozen. Now we have 4 bodies. This is add material and the extrude add frozen. Okay, the same thing, extrude. Okay, add frozen. Okay, 5 millimeters, just to be the channel for the air or the water or for any coolant. Just refresh. Okay, and then update. No, I'm gonna edit it to for named selections. Now we have 2 more zones, but for fluid, not solid, so be careful. It's very critical for you. So okay, this is mesh, can update it. Okay, fluid 1, fluid 2, and inlet 1, inlet 2, and outlet 1, and outlet 2. Okay, so the same zones, just we have just added, and here many more cells just to close, update. Okay, after updating we must reset the setup and open it. For double precision I'm gonna use 3 cores, and please wait. Okay, okay, transient and models, energy. Okay, here define models, add on module 8, enter. Welcome to MSMD. Enable. We're gonna use the same then 51. Like I said, you must be careful when you deal with these things. The same cell. Okay, zones, electric, negative, positive, cranberry system connection information to be sure of your battery. Okay, available material priorities or methods have changed. Please confirm the priority values before continuing. Okay, so we have here series 1 and burn 1. Okay, thanks. The materials like exactly what I have done. We're gonna use air for the coolant, but using water is preferable. Now the same thing, E material, active material for E. You must enter the same values. Okay, and here tin EOS E to the power 6. OS is the Arabic word. Now here 8 point, sorry. So gentlemen, we have used this information for without cooling simulation, so we're gonna use exactly like them. By the way, the values that we have just used for the first simulation are not as the same as values that were used for the tutorial. Here it was 678, not 871, but the density is right, and here is 18.4, not 202.4. I did not change them, I'm sorry, but that's why we found differences between the results. Okay, but it's okay. Anyway, we must use the same, okay, for this simulation to compare. Just we need to study the effect of the cooling here. 6 and here 9.83. Okay, no, and we have e-material and from database copper. So this is the simple idea. You must use the same material to get a good comparison. And here the user defined. T material, and here is 1. Okay. So we have used the same. Now go to the cell, active, fluid, it's gonna be air. You can add water if you want, air by default. For the tab, materials, T material, so the same T material. Okay, after this, for the boundary conditions, we have here the inlet air velocity. Suppose it is 0.5. Of course, it is a random value. You must know it from the experiment. And also we have, I can here say that suppose that the air enters at 16. So there's gonna be 289. Also can copy inlet, copy it, 22. Okay. So if you open inlet 2, you will find the same data. For the outlet, suppose it's greater than the atmospheric pressure by 0.1. And gentlemen, you must know or measure the outlet temperature of the air. Suppose that it will be 300 Kelvin. Okay, like the battery's wall. Just copy it. You must be careful. You must measure these values or guess them right, or use the analytical methods to calculate them. Now we have here the wall of the cell. due to the chemical reaction. We have here 5. Okay, we're gonna copy it to the walls. No, for the walls of the battery. Okay, not for the fluid. The fluid is the cooling fluid. Okay, now we have just finished this, and now this transient. Okay, solving equations. I need here the flow equation, and for the residuals, increasing this will make the accuracy better. We're dealing now with the electrochemical reaction that will generate heat and the fluid that will cool this. Okay, now go to initialize. Okay, excellent conversions, and run calculation. Now we may use 0.5 seconds because it's very simple. By the way, no need to decrease the time step, but you must test time steps to get better accuracy and validation, and compare it with the experiment. I'm gonna make it 5 thousandths and increasing this. Okay, leave it, and then you calculate have here x momentum, y momentum, and continuity, and that's why we need a very good mesh with a suitable time step to get the good conversions. To know if the solution is converged or not, it has to be 10. It has to be to the negative minus to the negative 4. Here is converged. Okay. -3, so it is converged. It is, or it's the way to the convergence, by the way. Okay, of course, you to compare between this simulation and the other simulation, you must reach the same time. Suppose that the total time was 600 seconds. So here, using this 0.5 second as a time step, you must stop the simulation at as minimum as or at 600 seconds too. Now I can tell you that there is a convergence here, and you will, of course, it will consume too much time until you reach 600 seconds. If the other simulation is 600 seconds as total time, to compare between the results. Okay. So now I'm gonna stop the simulation and start. Okay, of course the results are not accurate. Why? Because it is just a few steps, but I'm just showing you the temperature. Okay, so gentlemen, we have here this is the initial steps of the solution. We'll find here the temperature distribution. So the cell starts to be cooled or to cool. Okay, as the effect of the air. Okay, so I'm gonna show you the next simulation. Also can check out the other things like what we have just done. So the next simulation, we're gonna talk about modeling the pack, and I'm gonna show you more details about comparing the results. It's better to see it in the pack. We're gonna compare between the temperature and the current density. So now just ECM pack module. I have done it. Just duplicate it. I'm gonna show you how to make it in details. Okay, here we have a copy of ECM pack module. Let's see how to make the geometry. So we're gonna use the bus bar technique. We have here the active cell, and then notice that as material, and also we have here the bus bar is at frozen. Okay, those are the two important components. I'm gonna show you something. Okay, so we have here, this is the main components, the cell and material, and the bus bar. The bus bar was created in Autodesk Inventor as usual. Okay, and also you can make it simply here. Also you can hide this, and this is the bus bar. This is completely solid. Now after this I used the pattern technique, okay, to make a copy for the bus bar here. Okay, it is in the mid. Notice that if we divide this cell to two separate zones, it will be the same as the right is as the same as the left. Okay, after this we have done the pattern for the cell to copy them, to make a copy. Okay, okay, like this. So now we have three cells with 6 bus bars. Okay, it's very simple. After this, we create. I've carried out or I've generated a plane. I created a plane to from this face. I selected this face. Okay, to make a plane, just you can generate from XZ plane. Go to XZ, the X plane, and right click. I'm sorry, and click on this to generate a plane, and then new plane, and from face, and just click on this face to start sketching. Okay, so after this I created a sketch, and I drew a rectangle, and to make the bus bar by extrude command. The same thing for the other end of the plane. Okay, we have here the bus bar, or also you can simply create it in Venor. So here is the bus bar, and it is add material. Okay, and we have here also carried out the pattern, and then I translate this to here. So we have here the bus bar. It's connected to the so I'm sorry, gentlemen. This is the bus bar. The extrude command was created to generate the bus bar. This is the cell, and this is not the bus bar. This is the tab. I'm sorry. Of course, we have 6 tabs for positive and negative, and we only have 2 bus bars. So you can generate it from here, or you can use it in Autodesk Inventor. The same concept. Okay, so now we have here positive, positive, and negative, negative, and here positive and negative. So now this is positive and negative to connect between this cell and this cell. Okay, and here is positive, negative, positive, and here is positive, negative to connect between these cells, and we have here also positive, and here is the negative. Okay, okay, gentlemen, we have here the cell and the tab. Okay, this is the first thing you do, and then you can continue. Good. I'm sorry, this is not the bus bar, by the way. Okay, so close, and now I'm gonna show you how to make it. So we have to reset it. So we have here in this. You can find some tutorials, and we have here the mesh. I'm gonna make it random. Okay, generate the mesh, and for the quality, the maximum skewness. Okay, maximum, it's okay, it's not greater than 0.98. Again, this is the number of elements. Okay, so we have here 3 cells, 6 tabs, 3 negative and 3 positive, and 2 bus bars. Okay, so cell 1, cell 2, it's a body, cell 3, or the active zone. Now for the zones, we're gonna make it exactly like this. In tab zone 1, it's gonna be this. In tab zone 1, okay, in tab zone 1, for the negative, and for the geometry, all of them must be solid. Okay, we must see it solid. Okay, so after this is N1, and we have here this body in tab zone 2, and we have here in tab zone 3. After this, okay, positive P tab zone 1, okay, tab P tab zone 2, and P tab zone 3. Okay, so I have 3 negative and 3 positive, and bar 1 and bar 2. That's bar 1 and bar 2. Okay, and that's it. So you can see here where the tutorial. You can see here the tutorial. Okay, so the zones are here. In okay, cell 1, cell 2, cell 3. Okay, no problem. In tab zone and bar 1, bar 2. Okay, so please also must check on this solid, 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 solid. Okay, just close. Update. Okay, reset. Open Fluent Spiral 3. Okay, the last thing is tab in tab P. Positive. Okay, so this is tab P. Just the face. And here is tab N. Okay, update. Okay, reset the setup. Okay, spiral double precision 3. Okay, here we go again. Define models add-on module 8. Models MSMD enable. So we have here, you can specify system power. We're gonna make it to 100 watt. We're gonna leave this as it is, and the conductive you will find here. So the active is cell 1, 2, 3, and tab components, all the tabs, 6 tabs, zones, 3 negative, 3 positive, and only 2 bars. Electric, okay, negative, positive, and the most important thing, primary system connection information. Notice here that we have, of course, if you have any problem, you will know by warning message. So we have here Serial 1, Serial 2, Serial 3. Okay, so we have here series 3 in series, and okay, it's just one in parallel. Thank you. Okay. Okay, energy equation. Before doing anything, I recommend to check out if the zones are exist or not. Okay. And here are the materials. We're gonna use the E material for the cells. E 20 678 18.4. Edit for the negative. Okay. No. So I have here E and the copper. Now, okay, this is like the tutorial of Ansys. So we have here T material. User defined. Okay. Yes. Okay. Close. Now cell zones bar 1 T material, bar 2 T material. Okay. Cell 1 E material, E material, and E material. And for all the zones, T material. Okay. T material. the material. That's why CFD requires patience and accuracy to reach your target easily. Okay, and the material. Okay, the boundary conditions were the walls. Edit. We need all these walls. Thermal, convection. Also, I'm gonna make it 5 like the tutorial. Okay. And then copy. Copy to all the other walls. Okay. Yes. Just to close and go to transient solving equations. No need for the flow. Residuals. None. Okay. Initialize. Okay. Initialize it. Okay. Thanks God. No problem. But here I'm gonna show you a very important thing to compare between this simulation and this next simulation with cooling. New surface area. We're gonna make it here scalars positive and tap P to get the potential. Exactly like this. Notice that we used a different material. Okay. Okay, tap P. File into console. Okay. To compare between the temperature, volume, maximum temperature for all the zones. Profiles, plot, print the console. Okay. Then close. Then run calculation. Now calculate and initialize. Again, I have reset the simulation again. Because I faced the problem. So let's see what happened. For the temperature and the maximum magnitude of current density, I also added it. This is from my previous simulation, by the way. So let's see. Notice, gentlemen, that the temperature starts to increase. And here, this is the discharge. This is the my previous simulation. It works fine. And here is the maximum magnitude of current density. Okay, it will increase like this module from 300 up to this value. That's why we need cooling. And the current density increases by the discharging. Okay, and so on. Okay, so we're gonna stop it right now. This is my simulation here. The same setting, gentlemen, did not change anything. We also face problems with the projects that are used by duplication. So it is better to use the same settings as you see here. Okay, okay, no problem. And the cell zones. Okay, the same settings. Okay, and the boundary conditions for the walls. Okay, and here the monitors. I just added more monitor for the current. Yeah, this is the magnitude of current density to be used for the comparison. Okay, and that's it for this simulation. Now we're going to talk about the other simulation of cooling this pack. Okay, cooling ECM pack module. I'm gonna show you the steps to save time. This is from my previous tutorial simulation. We have here the same geometry, but I've just extruded. Notice. So we have here 1, 2, 3, 4, the same geometry, but I have extruded this face. Extrude. I've extruded the face to up to this face to be the cooling channel. Okay, and also this, and also another channel, and this channel. So we have here 4 channels for the cooling technique. Okay, we can make to know what happened. Okay, here is the cell, or it's as the same as the previous cell, but we extruded also here like this. Okay, this is exactly like the same previous simulation, but I extruded this. Okay, this face, and of course maybe add material at frozen. I'm gonna show you this is at frozen, and then it's 1 millimeter to fill this, and then I extruded this face like it, and this face, and like this face to be the cooling channels, and that's it. And then we close the geometry and go to the mesh. Okay, we have just here the 4 channels for cooling. of course, all these solids, solid, uh, but the new 4 zones, you may leave it as this, or you can make it fluid, doesn't matter. And here is the mesh. Okay, just update the mesh. Exactly the same zones, but we have here 4 fluids, 4 added fluids. So we have here fluid 1, fluid 2, fluid 3, fluid 4. Okay, and inlet 1, inlet 2, inlet 3, inlet 4 here. And here are the outlets in 2, 3, 4. And that's it. Just inlet and outlets for the cooling procedure. And you will use the same settings in Fluent, but add the material for the cooling, fluid, air or water, and then use the inlet boundary conditions and the outlet boundary conditions. Okay, the same thing models energy on and MSMD battery model. Please make the same settings. Okay, and also you can print system connection information. You will get the same information of the previous tutorial, previous simulation. Okay. Three series. And the materials, the same materials, but here I used water for fluids. Okay, for all the 4 fluids. And then the boundary conditions for the inlet. For the all inlets, I used 0.5 and 289. And for the outlets, for the 4 outlets, I used this. Okay. And then for the monitors, I used the same monitors. And then for the flow, air transient, solving equations, all the equations are needed with the residuals. Okay, and here the time step, and then calculate. Now we're gonna check out the temperature. Here is the discharge and the maximum temperature. Notice this is not 300 Kelvin, and here is the maximum density. Okay, and here is the first. Notice that it decreased, but slightly decreased due to the time step, small time step. And we have here the temperature increases, but slightly due to the time step. And of course, it is not 300 Kelvin. Why? Because the inlet water is 289 Kelvin. Okay, and so on. I'm gonna stop it right now. I'm gonna show you the results that I have generated. Okay, for example, this is with cooling and this is without cooling for the current density. Of course, with cooling, the current density increases. That's why we need cooling. So here the enhancement in the thermal performance of this cell was great using water, but if you use air, of course, you will not get this good result. Okay, I'm gonna close Ansys without saving. Why? Because I have overrated, oh, I'm sorry, overridden the solution that I have done. So I do not need this. So 14 and 17. Here for this Excel. This is without cooling. Okay, this is, I don't need this. I need the temperature. So this is the temperature, 0, 30. Up to try it again. Up to this second. Okay. With cooling, it's number 17. This is temperature. No. This is the voltage. Okay, here is the temperature. Notice it started with this, and here is the increase in temperature with the seconds, but now we have slightly increase in the temperature. Okay, due to the time step, of course. So let's compare between them. 3 seconds. Okay, to know the time. Okay, here is at 580. This is the temperature at 580. It's like this. So gentlemen, this is the temperature difference with cooling and without cooling. Of course, here is the enhancement, and like what we have just seen, the enhancement in also in the current density. So I think this is very good. Okay, now we're going to talk about another uh, design for the battery. We're going to talk about Tesla ECM module. It's like the design of Tesla. It is cylindrical. Of course, I do not have the exact dimensions, it's just a random model. And I'm going to show you only the steps that I have done. This is a method. I've done it using the extrude command. Okay, this is sketch of frozen add material, and here is the one extrude, and here is the third extrude. We have this solid, and we have this. Okay, so for the negative and the positive, add material and add frozen. This is add material, and the other to extrude add frozen. Okay, also you may not use this method. You can also you may use a very small extrude. No need to extrude all this the circle, just rectangle like the pack that I'm gonna talk about later. For the meshing, the geometry, solid, 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 must do it. Here is the mesh, run the mesh, and here is the cell, the tab, zone, negative and the positive, and tab N and tab P, and that's it. And you go to the setup, quickly open it. Here is transient models, energy on, okay, and here is the battery because it's single. Okay, the same setting of the first simulation, and the conductive zones, cell, and tab N and tab P, no bus bars, and the electric conductivity, electric contents, and here is the battery single cell. Okay, 1 and 1. Okay, materials, the same materials that we have done, and also the same thing, E material and T material. Okay, and the boundary conditions for the walls, wall cell, and I have 3 walls, wall cell and the wall tab, thermal convection. Okay, exactly for the second and the third, and we have here the monitors. Okay, also transient equations, no, flow equation, and residuals, no. Okay, and then you initialize, and thanks, and run calculation, 3 seconds. Okay, calculate, initialize. So we have here the potential, and the temperature. Notes temperature will increases, and here is the discharge, and is the voltage or area with average for potential phi positive V, okay, in volt, and here's the Kelvin. Okay, increases, and here it decreases. Okay, don't stop it. Here's the contours. Tap positive, positive, positive. Okay, and here is 3.39. Okay, and also you can see the negative. Okay, very fine. And for the vectors, current density, magnitude, like here for the current, and here the tap positive. Okay, this is for the walls. So see here is the current. Okay, is from here to here, can get new plane, hit 18, okay, so you can see here the current, and this is the current at this time step. Okay, of course if you let it calculate, okay, you can change the results. I'm just showing you how to model this kind of batteries. So here, gentlemen, increases the temperature increases, and here's the discharge. Of course, this is very good. Okay, we're gonna now close this simulation. And now we're gonna talk about the pack, and we're gonna use another method to simulate the single battery. So we have here, it's like Tesla. I'm repeating, I'm I'm assuring on that is not the exact Tesla ECM. It's like the any cylindrical battery. So let's open the geometry. So we have here, I have created it from this sketch, just a sketch, and then extrude. Okay, extrude, add material, and then another plane to make the sketch of the positive or this tab. I have here, okay, so we have here the simple. This is the battery, and here is the tab. Okay, the tab is just this box. Okay, no need to make the whole circle. Okay, and then we make the bus bar, and we have here also the other tab. If this is positive, so this the second is the negative, and just the pattern technique, the linear pattern, and then this is the bus bar. You can carry out the bus bar, create the bus bar here, or attach or import it. Okay, just very simple. Just extrude and sketch some sketches and some extrude, or you can import them. This is the bus bar. Okay, so two bus bars and one for negative and one for positive to make the series connection exactly. And just to close and go to meshing. And we have here the geometry. All of them are solid. Okay, and here is the mesh, and cell 1, cell 2, cell 3, cell 1, cell 2, cell 3, and here tab in zone 1, this, and tab positive zone 1, tab positive zone 2, tab in negative in zone 2, and tab positive zone 3, and tab negative, and tab in as the face will be this. Why? Because it's positive. Remember that it is here is this negative. Okay, this is negative, and here is positive. So why? Because this is the third, and it is this. Okay, this is the face, and that's it. And here the bus bar and the bus bar. This is faces. Those are faces, and these are body. Okay, bodies. That's it, and go. We're gonna open the solution. They're exactly the same settings of the pack. The same settings, general, transient models, energy on, and use the battery model, 200 watt parameters. Okay, of course, if you must, I repeat, you must use the same settings for with or without cooling. Okay, and here are the conductive zones and the bus bars. Okay, and electric contact and stage 3 in series and one parallel. Okay, and the materials exactly, and the cell zones and the boundary conditions, all of this data. Okay, exactly. Okay, and okay, we have here the potential, and here is 300 Kelvin. So we have here the temperature increases, and we have here the discharge. Okay. Okay, ladies and gentlemen, I hope this covers what you want. Now we can simulate a single battery with two different designs, and the pack of the batteries using also two different designs, and you can cool each one of them and compare your results. I wish this helps you. I'm sorry this tutorial is long, and you have here the data of that tutorial. Okay, please check out what I have just shown. Okay, and please study the heat transfer well and check out websites. It's not easy for the beginners. Oh, Li ion battery cooling, and watch YouTube videos, please. Okay, it's very important to know these kind of things. Thank you very much. I hope this helps you. Thank you very much.